Hello, and welcome to a brief introduction about infrared spectroscopy, also known as IR, and spectroscopy in general. This presentation was made for an introductory chemistry class where we've already talked just a little bit about organic chemistry structures, so we know what line bond structures look like and that there's carbons there. That's all you have to know to hopefully understand this video. Let's get started. So our first question that we want to discuss is, what is spectroscopy? Spectroscopy is the interaction of energy and matter to produce something called a spectra. So a spectra is a readout, so you'll usually see peaks, and the peaks are related directly to the energy and the interactions that are going on with the chemistry involved. All right, so it is nice to know if you're talking about spectroscopy that you may see these words either spectra or spectrum, and that has to do with whether or not it's plural or singular. That's the only difference. The spectrum itself is a readout of peaks that relate to the structure or sometimes other interactions of the molecule. Although it says that spectrums often look like a graph to people who have not seen them before, that's actually not what they are. So you don't want to think of them as terms of X and Y values so much as if you see a peak, that means something happened in the molecule that you'll want to know about. So you do need to know a little bit more about energy before we can talk about how the energy relates to molecules and how it interacts. So there are a lot of different types of energy, and these are on something called the electromagnetic radiation scale. So if you look at this diagram here, it says wavelength at the top. That has to do with the size of the energy waves, all right, because energy goes in wave patterns. So you may have seen this before if you've taken a physics class or something like that. So there's all kinds of energy. There's X-rays on the left here, and there's radio waves on the right. And as you can see, if you're on the left side, that's where things are very small. So they have low wavelengths. Those are in nanometers or smaller scale. And so that's very, very small, right? And then if you're on the right side, that's very big. So this could be meters. Like, for example, a radio wave can be taller than a human or taller than your house. It just depends on the specific wavelength and frequency. So hopefully that makes sense. Now let's move on to see how this relates to actual energy and the power of these different types of radiation. All right, so now as you can see, we have the same scale at the bottom, but now we're talking about the energy of these different types of wavelengths, right? So remember we said on the left we have the X-rays. X-rays were the smallest wavelengths, but if you look at the energy, they're actually the highest of the energies. That's because the relationship between energy and wavelength can be shown here in this equation. So if you look in the equation, if the number is small, that means you're dividing by a smaller number, which means the energy level should be big. So you don't have to know that formula. That's just to explain why small things have more energy and why large things have less energy, right? So if you think about it, X-rays are very powerful. You probably heard that before, right? You're not supposed to stand in front of an X-ray machine for a long period of time. People who work with X-ray machines have to wear special protective equipment if they're there all the time, right? On the opposite side, we have radio waves. Radio waves are not dangerous at all. They're so low energy that they would not hurt you, and they're not doing anything super dangerous to the molecule either, so that's good to know. In the middle, you'll see UV and visible light. Visible light interacts with your eyes, right? That's the kind that you can see different colors. And then if you look right around that range, there's UV light, which is right on towards the violet end of the visible spectrum, right? It's just slightly lower. And then there's infrared, which is slightly higher. Those are used for night vision goggles so that you can see in the night. That's infrared energy that you can see. They're like right outside of our vision, but if you have those goggles, you can use those. But infrared is slightly lower energy than regular visible light. So now let's talk about how the different energies affect how the electromagnetic radiation affects the matter itself. So as you can see, I've got the same diagram as the previous one. I just moved the different types of energy on the top, and I put what can happen on the molecular level at the bottom. So again, looking on the left side, that's high energy. So we'd expect dangerous things to be happening, and that can break bonds. So that could break bonds in your body, which again would be bad because then things could fall apart. If you talk about microwaves, if you've used a microwave for cooking, that actually rotates molecules. Specifically, microwave ovens are used to rotate water molecules. They're tuned to the energy that will do that job, and because there's lots of water in your food, it'll heat things really quickly. So if you've ever tried to microwave something that has no water in it, that's why it did never get hot, or it takes a very long time to get hot if it has a low water content. UV light, we know that UV light can be very dangerous, right? UV light is dangerous for your skin because it can damage your skin and cause skin cancer because it's affecting the DNA. Visible light, not dangerous, right? It's totally fine. It's specifically geared for your eyes to react. So your eyes know that energy level, and that's how they detect what type of light you see. So if you see the kinds that are the higher energy, and that means they're the smaller wavelengths, those are like in the violet range. And then the things that are less energy but in the bigger size, that is the red side. So it's like the Roy G. Biv, those different colors, that's how your eye does that. All right. So then infrared, that is related to heat, right? So that's a different type of energy and thermal. And then the NMR, remember we said radio waves were not very strong? They change something inside your protons, and only specific protons, and it changes the magnetic moment inside there. So it just means the direction of the magnetic pole that happens inside a proton. That is not doing anything permanent, right? That's obviously not permanent damage. So that's the lowest energy one that we usually talk about. So now that we have a general idea of how energy reacts with molecules, let's talk specifically about the types of spectroscopy that we're going to learn about. The main thing we want to talk about for spectroscopy is called IR. It's for the infrared region. The way that IR reacts with molecules is that it causes the bonds to vibrate. So if you have a specific energy frequency, it will cause certain types of bonds to vibrate. And that's how you're going to know what types of bonds you have in a molecule. Now, it does make a little bit of difference if it's symmetrical or not. So IR only vibrates not symmetrical stretches are the ones that you can see. There's other stuff for the other types. And it only shows you the functional group. So you're never going to know the exact molecule from the IR alone, but you can use it with other things, or you can at least figure it out and narrow it down. You can determine the functional groups. So functional groups, if you don't know what those are the parts of the molecule, an organic molecule, that make it do what it does. It makes it reactive. It makes it different from other types of molecules. So if you want to learn more about that, there's a separate video about functional groups that you can watch, or if you're in organic chemistry, you've probably already seen it before. But you always want to keep in mind that because it only shows you the functional groups, if you have two molecules with the same functional group, it'll be really hard to tell them apart using IR. You'd probably want to use a different method. So even though we're going to use IR to see the functional groups, we have to know that alkanes still show up. The alkane is the carbon part that doesn't really do anything, so we have to learn what to ignore. If you look at this specific molecule in the right, it's called hexane. So hexane is basically just an alkane. It doesn't have any special things, which you can tell because there's no letters being other elements, and there's no double bonds or anything like that. So that's the kinds of things we don't want to look at. So here's what the IR spectrum looks like. So if you look, it has a few things on the right, but the most important peak you see is right here on the left. But that's going to be in everything that has an alkane. So basically, we're going to have to learn to ignore that big blue one around 3,000, slightly below. Okay? So by comparison, here we have a different molecule. This is called octene. If you look on the bottom, it's a green molecule. So octene, see how it has that same big blue stretch around 3,000 that we're going to ignore? That's because it has all those carbon single bonds on the right. We're just ignoring those. But if you look, there's a very small peak that's right around 3083. That's the double bond stretch. So that's the key thing that we were looking for if we're trying to determine what it is. So that's a functional group. So those are the kinds of things you're going to look for. So if you're looking for something that's an alkene, meaning a double bond with carbon, or an aromatic, which is a different shape, then that's where you're going to see a key peak that you're going to look for. So above 3,000, it should be very small. Here we have a picture with the two previous spectra that we saw overlaid on top of each other. So as you can see, the blue one is the second one we saw, and the red one is the first one we saw. Most of the things are pretty similar, right? So if you look, there's that big peak that we're ignoring on the left, and then on the right side, there's some things that overlap, and then there's some key peaks on the right, but not as many. The one on the left is the key thing. The stuff on the right is called the fingerprint region. The fingerprint region is anything that's below 1,500. It's called that because, first of all, there's going to be lots of peaks over there, but they're really hard to pick out a peak because there's so many things going on. Usually you can't see what it is. Now, it's really like a fingerprint in that if I found your fingerprint at like the scene of a crime or something, I wouldn't know whose fingerprint it was unless I had your fingerprint already on file so that I could match it, right? So if I had the exact IR of another compound, it will exactly match, and then I could tell what it is. But unless I've already seen that compound before and have it in a database or something, I won't be able to tell just from looking at the fingerprint alone. Just like I couldn't tell if I looked at your fingerprint, I wouldn't know it was you unless I saw your face. Okay, so hopefully that makes sense. So we're kind of ignoring things that are to the right below 1,500. All right, so now let's get into the nitty-gritty of what specific functional groups you might be looking for your specific molecules for this assignment. So here's some functional groups that have no carbonyls. We'll talk about what carbonyls are before. But if you look, these are some of the options. So there's this ring here. That's one of the functional groups. That's called an aromatic. There's an alcohol that has an OH. There's an NH2. That's an amine. And then at the bottom, there's a couple of different functional groups on that one. But if you look, none of these have a carbonyl. So when we get to that section, you can tell them apart. Another thing you want to do before we get too far is make sure that you have a handout that has the listed peaks that we're looking for. There's numbers that go with each of these peaks and their shapes. So I'm going to show you the shapes, but for the numbers, you want to look on the IR handout. For Dr. Cossey's class, you always have a handout that has the numbers, so you don't have to worry about those, but you want to make sure you get that. So if you look in the bottom corner, there's a little picture of what you may have. So it should look something like this. So on the left, it'll say the name of the thing. It'll have a picture of the bond you're looking for, and then on the right, it'll have the numbers where you're going to look. Okay, so make sure you have that available. All right, so one of the big easy things to see on an IR is if you have an alcohol. So an alcohol has two key peaks. The most important peak is probably this one on the left. You guys haven't seen that before, right? So if you look, it's a peak that's above 3,000 and it has a very broad shape. It's very rounded. So it looks different than all the other peaks, which are more sharp and spiky, right? So an OH is always going to look like that. Now, sometimes if you have a peak that has water in it, it might look a little bit like an OH, but it'll be much, much smaller compared to the size of all the other peaks. So we won't have to worry about those. So if I knew something was an alcohol and I was trying to label it, I would label two key peaks. Firstly, I would do the one on the left, the one that's above 3,000, this one right here. That's the OH, so always label it as if it's the bond. So the bond that we're talking about is the O to the H bond. The other peak that is a key peak is the CO bond, right? There has to be a carbon attached to the oxygen, otherwise it might be like water or something. So if we're looking for a peak there, it says on your chart that it's between 1,000 and 1,200. So just look at the 1,000 to 1,200 and whatever the biggest peak is, point to that and then write CO. And those are the two peaks that you need for an alcohol. Now, again, just as a reminder, you're going to get those numbers from the chart that you're given, the handout. So I put right here the little piece of the chart with the OH, for example. So if you look here, it says OH stretching, that's the OH bond, right? And we're going to use this number here where it says alcohols and phenols, that's 3,200 to 3,550, right? And that's within this range because it's right here, right? So then that's how we know it's right. So again, you'll have the handout. I won't show you every time, but I just wanted you to remember to correlate those to the chart so you don't have to memorize the numbers. All right, so now I'll show you another type of functional group. So another one's called an amine. An amine means it has nitrogen bonded to carbon with single bonds, and there's no double bonds around it. So that's an amine over here on the right. That's heptylamine. So the peak that you're looking for, if you look on the chart, it says it's also above 3,000 like the alcohol. But if we look at that region, you notice it's this peak here, right? That looks different from the alcohol. How is it different? It's a different shape, right? So it's not a different place, but it's a different shape. So again, we're going to have the same sort of number range, but it's going to be kind of this lumpy shape. If you look, that's how I describe it, as it's broad but lumpy. So it's wider than a normal peak, but it's not as rounded as the OH is. Okay, so that's how I would describe that one. That's the peak you would label. You only have to label the NH peak for this amine. That's all you need. All right, I would be remiss if I did not point out one more thing about amines. There are different types of amines. If you look here, there's 3 different types. There's one on the top has 2 H's, the one in the middle has 1 H, and the one on the bottom has 0 H's. So there's a different number of bonds to H depending on if there's bonds to carbon instead, right? They all have 3 bonds, things on the nitrogen, but it's just some of them are hydrogens and some of them are carbons. So for the first 2, you notice there is a peak in the 3,000 range. The shapes are different. If you look, the one on the top is primary. That's the shape we just saw. The one in the middle is called secondary. It's a slightly different shape, right? It looks more like it's got a pointy finger, but it's still kind of rounded. And then the one on the bottom doesn't have a peak there because there's no NH, which is the key peak we're looking for. So I won't give you any like the bottom anyway, so you don't have to worry about those. All right, so we're going to start going a little bit faster through these, hopefully. But if you look at the next one, this is called an ether, right? An ether is a carbon-oxygen-carbon bond, so no H on there. So it shouldn't have an OH peak, which it doesn't. So if you look at that, you're going to have to look for a CO bond, which is something we saw in the alcohol, but it'll be missing the OH peak, and that's how we'll be able to tell them apart. So remember we said if we look on the range on the handout, it says it's 1,000 to 1,200. So we're going to look in that range and see if we see a peak that's really big. You see it? Yeah, it's right there, right? It's kind of right at the edge of the 1,000. So that's the peak we're looking for. Now this one has another functional group. It has these double bonds that are in this like hexagon shape, right? That's called an aromatic. So you'd also want to label that functional group as well. So the ether key peak is the CO peak. That's all you have to label. But this one just happens to also have a double bond. So that peak right here would correlate to that aromatic. Okay, cool. All right, so we're going to pause the video here, maybe take a little break if you need one, but you do need to watch the part 2 of this video. That's where you're going to see all the other functional groups, so you're probably required to have those, so make sure you check that out. Hope this is helpful. Bye, thanks.